Thanks very much to Beatrice for the invitation. So what I'll talk about is joint work with all these people listed here. So Matthias Weigelberg, who's in Vienna, Alexander Cox from Bath, Martin Hüßmann, who's in Bonn, and David Prömel, who's now in Zurich. And I'll tell you right in the beginning the result that I want to get in the end, and then I'll start a bit with the history, motivation, and how we derive it actually. So the situation in which we are is we're given, there's some asset, and we want to price some derivative on that asset, and we assume that we know prices of simple call options for a number of maturities, 1 to n, and then we know all strikes. For all these call prices we know. And so we know them because they're liquidly traded, so we can invest into the asset or we can invest into these call options. And now we want to, with this, we can somehow try to hedge a complicated exotic derivative, and we want to hedge it in such a way that we eliminate all risk. So we want to find a pathwise hedge. So there are no models also really, no matter what happens, we want to be absolutely secured. And this will then be an absolute upper bound for the price that we could possibly put. I mean, we will not be able to sell it for that price, but this will be really the absolute, if we were able to sell it for that price, we would really completely eliminate all risk because it's completely pathwise. And so this is the result that we have. And like I said, so we'll then start again slowly, just so you know where the trip is going. So if the derivative is of the following form, it depends on the volatility, the quadratic variation at these different maturities where we know the call options. And it depends on the entire trajectory of S. So T of S is the entire trajectory of S, except that you reparameterize it in such a way that at time T, the quadratic variation is exactly T. Okay, so maybe you have to stretch it a bit or you compress it a bit. But basically, it's the entire trajectory, except that you reparameterize the time. So it's not running in the physical time anymore. And then we have this superhedging price, or you try to superhedge using trading into this asset and into these call options for which we know the prices. We assume that they are there, so we can buy them. This price is given by the supremum of the martingale expectations, where you take all martingale measures that reproduce the call prices that you observed on the market. Right, so I'm not sure this is a very useful result for applications because these two values, they are the same, but they will be huge. So they will, for practical things, if you want to sell anybody any derivative for that price, they will not buy it. But I think it's mathematically very nice because here really you get, so as a probabilist, I like martingales. And here you get martingales out of nothing. We don't start with any probabilistic structure. We don't impose any model, nothing. And in the end, still we get out martingales. So this, I think, is a really nice result. Okay. Now, so this will be the end of the story. And now let's start from the beginning. Let's start with the very classical. What do we know in classical math finance? So what you would usually do is you assume you have a stochastic process that is a model for the evolution of your asset price. Okay, everything is discounted, there are no interest rates. And the first thing then you do is, and we've seen actually many talks about this in the past days, is you try to examine under which conditions is this stochastic model. Okay, it's just some stochastic process. In general, it will not be a good model for asset price evolution, and you try to figure out what are qualitative assumptions you should put. And what do they tell you about the structure of the model? And this leads to these fundamental theorems of asset pricing. And the final answer to that was given by Delban and Schachermayer. Okay, so everything here is continuous for me, so we're locally bounded. So we're in the Delban-Schachermayer 94 setting. So it is a reasonable model if and only if there exists an equivalent local martingale measure. Okay, so then you can weaken that later, get to this NUPBR. We'll talk about that a bit later, but let's say, so if you impose no free lunch with vanishing risk, you get these equivalent local martingale measures. Okay, so we have the martingale measures, and then the next thing you can observe is if now you want to price some derivative, so the derivative is just some random variable, then the minimal superhedging price, so here you just superhedge trading dynamically into the asset, is given by the supremum of the martingale expectations. There are two important things here. we superhedge almost surely under the given probability measure that we have. So it's really it's outside of a null set, we only have to superhedge. And the second thing is we take the martingale measures which are equivalent to the measure from which we started. Okay, and so I'm not really an expert on finance, so this is my naive understanding what's problematic with that. Maybe there are people in the audience who understand this way better, but so from my naive point of view, this does not secure you really against all risk because you don't really know what the model is. Okay, so in physics we have laws of nature, we have first principles from which you can somehow derive a model. In economics it's too complex, this maybe doesn't work so well. I don't know, maybe it does, but from my understanding it doesn't. And in physics we derive a model and we derive it from first principles, but even then we can still make sure that it is the right model because we can do a controlled experiment where we can really control all the external influences. And economics is of course way too complex, so we cannot do that, so we can never be absolutely sure that we have the right model. And even if you say, okay, for some reason I believe this is the right model, for example, Black-Scholes is the right model, well then there are parameters that you don't know, so in the very least you will have model uncertainty. Okay, so how do we get the model? One thing you can do is, so let's say we take now a Black-Scholes model, and then I think this goes back to Dupier, maybe not. But so you can see that European call options are actually very liquidly traded, so you can infer the prices from the market. And if you know the price for one European call option, and you assume you have a Black-Scholes model, this tells you what the volatility is. And when you know the volatility, you know the entire model, you can price all derivatives. Right? Okay, this is great. But of course, then you apply this, you have several prices for call options in the market, and you get this volatility smile because they're actually not consistent. So the implied volatility is not always the same. So you cannot extract a model from that. So what Dupier observed in '94 is that, okay, let's assume we know all call prices for all strikes and all maturities. So you have a surface, right? So you have a two-parameter thing, strike and maturity, and for each you get a value. So you have a surface. Assume we know this surface and some mild non-degeneracy conditions are satisfied. Then you can find a unique model which reproduces all these call prices and which is a diffusion, so it's a Markov process, and it's a martingale. Okay, so for pricing, you remember we had these martingale expectations, so we don't really care about, so we only care about the martingale measure. So this gives us a good model, and now we can price other derivatives. Okay, but then again, somehow for me it's not clear why prices should follow a martingale diffusion. It's very elegant mathematically, and you do get a good model. It works nicely, but so conceptually for me it's not clear. Where do you get this from? Why should it be a martingale diffusion? Why not something else? Okay, and then the model-free approach tries to eliminate this, tries to not choose one specific model anymore. Or okay, we'll see in a second, you still choose a model, but it's somehow adapted to the situation at hand. So, yeah, in the model-free approach, you now say you don't want to hedge anymore with respect to a null set, outside of a null set, but you really want to superhedge on all continuous paths. And we assume again that call prices are known, but we only assume that they're known at the terminal time. Not anymore the entire surface, but at the terminal time we know all strikes. And so we can superhedge trading in the asset and in call options. And what you do, what Hobson does then in a list of papers, I'll get to that in a second, is to show exactly such a superhedging duality. So the superhedging price in this sense, the pathwise really, all the risk eliminated, is given as the supremum of the martingale measures, where you look again at all the martingale measures. You know the call prices at the terminal time, so they have to reproduce, the martingale measures have to reproduce these prices. So you restrict the set of martingale measures that you consider. And if you want to show such a duality result, as always in this stuff, one direction is easy, it's completely trivial. And this is that this is larger than the supremum. And this one is quite tricky, and It is shown by finding one martingale measure which is optimal. So by finding actually the optimizer here. And this is done by the Stochastic embedding problem. I'll give you an example with more details in a second. So, but this then has been applied to really a bunch of different derivatives, G. So the first work of Hobson was where G is the maximum, so it's a look-back option, the maximum of that your trajectory achieved during the time. Then in Hobson-Pedersen in 2002 looked at something called forward start digital options. So you look whether your trajectory crosses a certain level in some time interval in the future. Not starting today, but maybe between tomorrow and the day after tomorrow. You look if in the day it somehow crosses a certain barrier. Then options on local time in Cox, Hobson, Obloy. I don't know if options on local time are traded or not, but okay, so the theory works on that as well. And then there's lots of works on different options on variance. I'm just listing two here, but there are really many, many papers on that. So Davis, Obloy, Raval, and Cox, Wang, where, yeah, so the F is of this form. It's some function of the integrated volatility of the log price. Okay, so of the quadratic variation of the logarithm. And then there's a bunch of other papers where they do the same approach. Okay, let's look in one particular simple case at how this argumentation works. How do they do it? So we want to price a one-touch digital barrier option, I think it's called. So this TB is the hitting time of some level that is higher than where you start, otherwise it's trivial. So you're interested in whether at some point during the time interval you look at, your trajectory gets across a certain level. So it's the same as this forward start digital option I showed before, except that now you don't start forward, you start today. And so this is by a paper of Brown, Hobson, and Rogers, what I'm showing now. The first thing they do is they observe you can get a pathwise inequality for this thing you want to price, bounded from above by these two expressions. Okay, so I don't want to say how, I mean, okay, so you can just verify it for yourself. The left one just takes two values, either 0 or it's 1, and in both cases you check and the inequality is true. So there's no miracle happening here. But then what do we have here? So this here is the payoff you get from a call option times some factor. And this here is what you get by short selling at the time when you hit the barrier, 1 over b minus k units of the asset. Okay, so this one you can buy for free. You don't have to pay, you don't have to start with any endowment to begin with. And this one, well, for this you have to pay the price of the call option divided by b minus k. So the minimum superhedging price should certainly be lower than this thing here, right? So first of all, this works for every k less than b. So for every k less than b, it should be less than this. This is the price of the call option. And now you can take the infimum because the left-hand side doesn't depend on k. Okay, so you have an inequality. A priori, it's not clear how useful this is. It could be way off, could be way too big. And now, so far it was completely elementary, and now they bring in heavy tools, so to say, but really crack the problem then. Because now they use the Stochastic embedding problem to find the martingale measure which reproduces all your call prices. So it is from this set MMP that we had before, over which you're trying to solve the maximization problem. And actually the expectation of this random variable G you're trying to price is exactly this infimum. So they actually construct the optimizer for this problem. And they show that the inequality they derived here is, well, it's of course not always sharp, but in the optimal case it is sharp. Okay, and yeah, from that you get the duality, because if you have any martingale measure that reproduces the prices, then you can always see that the expectation must be less than the minimal superhedging price. This is what I said, this is the easy direction in the duality. And so therefore the supremum must be bounded from above by this superhedging price. But on the other side, well, the superhedging price is bounded from above by this. And we found one martingale measure where equality is attained. So in the end, they derive that, well, you have the duality, and in fact, you know the value of the optimizer. So even more, you don't only derive the duality, but you actually calculate the value, and now you have the upper bound for your price. You're happy. Okay, so this is a very nice mathematical approach and it really works for a lot of problems. One downside is you really need to, if you want to price a new derivative, you need to write a new paper. Okay, so for every single one, you need to do a new argument because if we go back, the measure P that they find here depends specifically, it will be tailored to this specific G here. And here they apply the Stochastic embedding. So if you have a different G, it will be a different measure. You need to somehow find a different solution to Stochastic embedding. And so you need new arguments. Okay, so it would be nice to have something systematic where you can get all G at once. And this was done by Duality and Soner in 2013, who are in the same setting as Hobson and all these papers before. So you know the call prices at the terminal time. And they assume that G is anything, so now it's abstract, it's not something concrete, but it should be Lipschitz in the call price. It should have a Lipschitz in the asset price. So it's some functional from trajectories to R, and the functional should be Lipschitz continuous in the trajectory. And then they get that, well, the duality result that we want. The proof is based on martingale optimal transport and this really beautiful mathematics. And in a 2015 paper, they greatly generalized that. So they can do jump processes, they can do RD value processes, so everything so far was one-dimensional. They can include multiple margins, so here is always just, I wrote here that the prices at the terminal time are known, but in fact you can include as many margins as you want. You can include partial information, so you don't know all call prices, but only finitely many, let's say. So really they can do a lot. And they can even relax the Lipschitz continuity assumption, but they still need to be uniformly continuous in the sup norm. The dependence on the path still needs to be uniformly continuous in the sup norm. Okay, and now we go back to what could be done with a Stochastic embedding approach. And we see that none of these is continuous in sup norm essentially, except the first one. Okay, so if you have so this is a continuous function in a subnorm, that's okay. But such hitting times, they're not continuous, right? So you can have two paths that are arbitrarily close to each other, but one gets across the barrier and the other one not. So it's not continuous at all. Local time is of course not a continuous functional because you can approximate Brownian motion by smooth paths. And quadratic variation, same thing. So you can approximate Brownian motion by smooth paths, so quadratic variation is also not continuous in the subnorm. So it's somehow orthogonal to the works of Hobson and all the works that followed. Right, so the aim is, that's then where we come in. If we can somehow if you can somehow use this Stochastic embedding approach to get a result that is similar in spirit to the ones that Hobson and so had, but that has the generality of, the systematic approach of Duality-Soner, but allows us to take something which is not uniformly continuous in subnorm. And so this is the result I showed you in the beginning, and we'll derive it now. And as the first thing, I want to introduce game-theoretic martingales, which are an important tool in the proof and which I think are a really nice theory anyways. And then in the end, I'll show you, if you never heard Stochastic embedding before, if you don't know what that is, I'll also explain that in the end, as I show how to combine them. These two. Okay, what are game-theoretic martingales? So this is something that was introduced by Vladimir Vogt in 2009. And it's basically, there's nothing to it really. It's just pathwise superhedging, nothing more. So we assume again, we have a space of trajectories that model the evolution of some asset price. So called omega, these are the continuous paths from 0 infinity to R. S will be the coordinate process. So this is now our price path, let's say, but it can be any continuous function. Then we define simple strategies. They are just what you would expect, buy and hold strategies, like in the classical setting. Because to define those, there's no probability measure here, right? So we don't take any expectations or so. But to define what a simple strategy is, you don't need that. So you can do that in a pathwise sense. And if you have a simple strategy, then this stochastic integral, which is just a locally finite sum, is always well defined. It's some real number. And then we say, a strategy is lambda admissible for some positive lambda if this value is bounded from below by minus lambda for all omega for all t. So no matter what happens, no matter at which time, you never lose more than lambda. And of course you can, so remember we have continuous paths, so we can make any strategy lambda admissible by simply stopping when we hit minus lambda. Okay, so there's nothing to it. And what Wolf then defines, and actually this is not the definition of Wolf, I give you a slightly modified one that we gave with David Prömel, but I mean it's very much inspired by Wolf, only modified slightly, is we define an outer measure as a pathwise superhedging price for the indicator function of a set. Okay, so it's a bit much to get your head around. So let's take some set of the continuous path. Then we define the outer measure as the smallest lambda, ignore the lim inf for now, for which there exists a strategy which is lambda admissible, so that if I start with lambda, I invest in this strategy, then in the end I get at least 1 pound whenever I'm in the set A. And if I'm not in the set A, well, I still have at least 0. So I didn't lose more than the lambda I started with. This would be the ideal definition. So you just take one simple strategy and you define superhedging in that way. That would be economically perfectly meaningful. Thing is, we cannot do any math with that. Okay, so you have to do something more. If you want to derive interesting properties, you have to somehow relax it. And this is where Wolf and we come in and where we do it a bit differently. So we take here a lim inf, so like a worst case scenario along a sequence of simple strategies. This is, it's a bit difficult to interpret because you're not saying you trade with one strategy, but you trade with a sequence of strategies and then you see somehow what happens in the limit. But with this we can do math. So it's so the lim inf here somehow in some situations allows you to apply Fatou's lemma, and so it's something which is useful in probability theory normally. Okay, and then what Wolf would call game-theoretic martingales are these processes, these simple capital processes. So where you invest with a lambda admissible strategy and you look at the gains you get. And correspondingly, so if this is a game-theoretic martingale, then this lim inf here will be a game-theoretic super martingale. Because if you have a sequence of positive martingales, then the lim inf will be a super martingale. Okay. So some object that you can define. Let's see if it's useful. And the first observation, which is due to Wolf, is that if you take, so the outer measure was defined for any subset of my continuous path. Now I want to compare it with probability measures, so the set better be measurable. So let's take a measurable set. Well, then the supremum of the martingale expectations is bounded from above by this outer measure. Okay, so we have constructed one object which is simultaneously larger than all martingale measures at once. And this is again a two-line proof, like the easy direction in the model-free approach I showed you before. Second thing is, and now we get to this NU PBR, no arbitrage of the first kind. Let's say we have a set that has outer measure 0, so where this P bar of A is 0. So this means you start from an arbitrarily small epsilon, and on the set A, in the end, you get 1 pound. Okay, so you can imagine you scale the thing up. If you start from 1 pound, then in the end, you get basically infinitely much. There's a small gap here. You still have to, you can get arbitrarily much, and then you still have to see that you can get infinitely much. But indeed you can. So a set has outer measure 0, if and only if you can find a sequence which gives you infinite profit starting from 1 pound, and you never risk losing more than the 1 pound you started from. Okay, so no matter what happens, all scenarios leave you at worst with 0, and on the set A you get infinitely rich. Okay. And clearly such a set should somehow not occur. So these are paths which you can maybe exclude when you try to do model-free financial mathematics, right? Because these are too good to be true. And here's the link to the NA1 measure. So we saw this several times. A measure satisfies NA1 or NU PBR if this set is bounded in probability, where we take the one admissible simple strategies at infinity. And I mean, if you compare these two, bounded in probability, and here the lim_inf should be infinite, you can believe, and it's not hard to show, that if you have a measurable set that has outer measure 0, then whenever you take a measure that satisfies NUPBR, it assigns also probability 0 to this set. So what we do here under this p-bar is quasi-sure analysis for all these NA1 measures. Right? And that's good because, okay, we saw this in many talks in Platen's talk, in Rungalier's talk, and also in Bayraktar's talk, that NA1 is really the minimal assumption that any model has to satisfy. If you take a model that doesn't satisfy NA1, then any investor can get infinite utility. And so infinite maximal expected utility. And if you have some unbounded utility function for which the investor can get finite maximum expected utility, then you already satisfied this NA1. And so I think the first work where this kind of results were shown is in Ankirchner's PhD thesis, and then Karatsas-Kadaras generalized that, and then, well, there were lots of other papers. Actually, I'm omitting many here. But so the nice thing is, if we show something under p-bar, it holds for all these measures, and the rest of the measures, they don't interest us anyways because they're not relevant for math finance. Okay, so we say a property holds for typical price paths if it is violated on an offset. So, okay, so again, this takes some time to get used with. So what does it mean? So for example, if I say typical price paths are not differentiable, are not differentiable at 1, let's make a simple case. Then this means that you can start trading with £1, and whenever the market throws a path at you that's differentiable at time 1, then you get infinitely rich with this sequence of strategies. And if any other path comes, okay, well, then you are out of luck. You lose maybe your euro or your pound, but that's it. You don't go you don't go negative. So really these paths, atypical price paths really shouldn't occur, so you shouldn't worry about them. And what Wolf observed is that typical price paths have a quadratic variation. And they have finite p variation whenever your p is larger than 2, and they have infinite p variation whenever your p is less than 2, so just like a semi-martingale. And they have no points of increase, for example, and he showed lots of other things. And together with David Prömel, we showed, we showed that typical price paths are rough paths in the sense of Terry Lyons. We showed that they don't only have a quadratic variation, but in fact they have a nice local time, which is as nice as you could hope. So it's as nice as the Brownian local time. And it clearly cannot behave better than anything under a martingale measure, and particularly not better than for the Brownian motion. So it cannot behave better than the Brownian motion. So this is the optimal result. And we also managed to set up a stochastic calculus where we have an E2 integral and so based on these typical price paths. But the best result in this entire approach is due to Wolf, and this is really an amazing result. It's the pathwise Dambis-Dubin-Schwarz theorem. So Wolf defines a time change operator, so I told you typical price paths have a quadratic variation. Okay, so you can talk now about the quadratic. So if you look at the set of all continuous paths, well, nearly none of them will have a quadratic variation. So the set of paths with quadratic variation is very, very poor in the set of all continuous functions. But now for the typical ones, it is there. So Wolf defines this time change operator, which turns the quadratic variation at time t into t, so makes the quadratic variation linear. And then he shows if you take, this outer expectation is defined like the outer measure was, so pathwise superhedging. So for non-negative f. If you have an f that only depends on the reparametrized path, so on the one that has quadratic variation t at time t, and you restrict yourself to paths starting from a given initial value and where the quadratic variation doesn't die down, then you can actually calculate this superhedging price, and it's just the expectation under the Wiener measure. So this, I think, is really a beautiful result. So the Wiener measure, really, this one probability measure of the Brownian motion comes in completely out of nowhere. So you just by trading arguments, you get the Brownian motion. And this is what we'll use then to derive our result. Okay, so now this is the tool of game-theoretic martingales, and now we want to use this to prove the duality that I showed you in the beginning. So what do we take as our setting? I'll show you the one marginal case just because it's less technical to present. So we look at all continuous paths on the interval 0, 1 with real values, one-dimensional. This is important. I'll get to that in the end. And okay, so today we know the initial value, so at time 0, they start in 0. We assume that we know, well, European calls at the terminal time are frequently traded, so we know their prices. And actually, it turns out if you know all the call prices at the terminal time, then they determine a probability measure. Okay, so a family of call prices, of infinitely many call prices, determines exactly a probability measure, at least if they're arbitrage consistent. Otherwise, okay. Anyways, there's nothing to do. So this means we know the distribution, the marginal distribution of the price at the terminal time, and this is just this probability measure which corresponds to the call prices. And now we want to price an exotic derivative, and an exotic derivative for us is a functional that takes the trajectory of our path and sends it to a real value. And our primal problem, so we want to show a duality problem, so I introduce a primal problem, a dual problem, and then I want to show that the values of these two optimization problems are the same. Our primal problem is to find the supremum of the expectation of G under all martingale measures for which S1 has the given marginal distribution, which just means all martingale measures that reproduce the call prices that I already know. Okay, so we just want to find the maximal martingale expectation. That's our primal problem. Our dual problem is this superhedging problem. So we define simple strategies exactly like they were defined before. So buy and hold strategies, pathwise defined. Everything is okay. We introduce a set of admissible strategies. I don't want, this is technical, what admissibility means here, but let's ignore that. So there's some admissibility condition. We need to exclude doubling strategies. That's the main point. Okay, so you need something that forbids doubling strategies. And then we have a set E, which are the European prices which are available for free. So, okay, so we take continuous functions which integrate to 0 under this pricing measure at the terminal time. So this means if you have a derivative that pays psi of S1, then you can buy this, you can get this for free. And then the dual problem is to find the minimum superhedging price where you do dynamic trading along such a sequence of strategies again. This is crucial, so we have to take such a sequence. We cannot write down a pathwise integral here, really, because we're looking at all continuous paths, so there's no stochastic integration also, right? So we have to, you could take bounded variation paths or simple strategies or so, but so we take these lim-infs of simple strategies. And then we can also buy such European options which are available for free. Okay. If you buy something which is not available for free, then you subtract the expectation from that. And then we want to be larger than this G, which is our exotic derivative, and we want this omega by omega. So again, complete elimination of risk. Okay, and now we assume that G has a certain structure. We assume that it's some gamma, which depends on the quadratic variation at the terminal time, and on this renormalized path. So this is Wolff's time change, which turns the quadratic variation at time t to exactly t. And so here it's written again. Okay, this is the theorem. If the gamma is upper semi-continuous and bounded from above, then the two values, the primal optimization problem and the dual optimization problem, have the same value. And so related works are the works by Dolinsky and Sona that I already mentioned, and then there's work by Hu and Obloy where they generalize Dolinsky-Sona. This is in the model-free setting, so really in the omega by omega setting. What you can also do is quasi-Shor analysis. So you don't say, I want to do this for all omega, but I want to do it quasi-Shorely under all martingale measures. And so this is something different conceptually. In the end, it will come probably to the same results, but conceptually it's very different if you say I want to do it for all omega or quasi-surely under all martingale measures. But so in this quasi-sure setting, there's a whole bunch of literature, which I won't list all, and I don't know very well, but there's one paper which is very, very similar to this one, where basically the same result was derived in a quasi-sure setting rather than model-free by Guo Tantuzi at the same time. I think the papers were on the archive within a few weeks of each other. Okay, now let's look into the proof. So again, the easy direction. How do we show that? So we want to show that the primal problem is bounded from above by the dual problem. So we take anything which is larger than the one in the dual one. So the dual one is the pricing problem. The primal one is the expectation problem. We take something which is larger than the D. This means that we can find a superhedge starting from this P. So we find a sequence of strategies. We find such a psi which integrates to 0 such that we have this pathwise inequality. Well, if we have that, it's an omega by omega inequality. So if we take expectation on both sides, then under a martingale measure, or under any measure, it will still persist. But if we take a martingale measure where S1 has the right definition, the right distribution, okay, I don't know, this should be S1 of P here, then, well, we apply Fatou's lemma once and pull this out. Have this here, this is a local martingale now, which is bounded from below in some sense. Okay, so this is bounded from above by 0, and this is 0, so we get that we're bounded from above by P. Okay, and now the interesting direction, and there we use again score-dot embedding, and now I'll tell you what score-dot embedding is. So if you have a Brownian motion, and you have any probability measure which is centered, so in particular it is in L1, right? So I mean it has a finite mean, finite L1 norm, and it integrates to 0, then you can always find a stopping time such that the Brownian motion stopped at this stopping time has the distribution you want, and the process is a uniformly integrable martingale. So this is, yeah, it goes back to Scout-Hot. I think Scout-Hot had the assumption that the random variable also has a finite second moment, but in fact this is not actually necessary. So you can then relax it. Okay, now you can make a simple observation. Now we can apply, so I told you there's a Dunby-Stubin-Schwarz theorem, which is pathwise due to Wolfk. But of course there's also the classical Dunby-Stubin-Schwarz theorem that tells you if you have a martingale and you apply this time transformation, which turns the quadratic variation at time t into t, well then after that you have a local martingale with linear quadratic variation, so it's a Brownian motion. So this process is a Brownian motion and it's stopped in the point where the quadratic variation reaches 1. And then you can see that this is a stopping time in the time change filtration. Okay. So this is a very simple observation then, that the primal problem we started from, so to find the optimal martingale measure, can actually be rewritten as finding an optimal stopping time for a Brownian motion. Okay, so this is now a different primal problem. So we want to find the supremum of the expectations over all Brownian motions and all stopping times. So what does it mean, all Brownian motions and all stopping times? So you can in particular take a huge probability space and where the filtration is much bigger than the one generated by the Brownian motion, and the stopping time is a stopping time in that filtration. So it doesn't have to be a stopping time in the filtration coming from the Brownian motion. Okay, so, and recall that this gamma here is just a different way of rewriting the G that we're actually interested in. Okay, so now we rewrote our primal problem, now we rewrite our dual problem. And then in the end we link these new primal and dual problems. And this is from some very nice work in which I'm not involved, but by the first 3 authors of our paper, so Beigelberg, Cox, and Huisman, who have a really fundamental new work on the Scout-Hot embedding problem, where they somehow systematically study the optimization problem associated to it. So this optimization problem that I showed you here, they really study this as a systematic problem. And they show that they have a duality result for that. They can link it to some different dual problem, which consists in finding, okay, so again, somehow a psi here, a function that integrates to 0, And now a very nice martingale under the Wiener measure. Okay, so finding this optimal stopping time can be translated into finding an optimal martingale and finding an optimal European option in some sense. In such a way that you still superhedge the thing you're interested in. But note that here now we have gamma of omega, and before gamma never appeared alone. It was never gamma of omega, it was always gamma of this time-changed omega. So this here is before the time change. So now what we need to do, we simply apply the time change on both sides, still have this inequality. Okay, so we have this thing here, this looks good actually, this is something we can trade in, this is this European option available for price 0, so this is good, this is also in our dual problem, this plays a role. And this thing here is still very, okay, so it doesn't fit into our framework at all. But now, actually all we need to do is, so this looks tricky, but by a relatively simple argument we can apply Voft's theorem, Voft's pathwise Dambis-Dubin-Schwarz theorem, to find a sequence of strategies that give a pathwise superhedge for this martingale. And then we get that D is bounded from above by D star. And well, for this we know from this paper that it's equal to P star. And we just show that P star is equal to P, which is a simple result. So this gives us the inequality D is less than P, and P is less than D we already showed, so we proved equality. Okay, so some remarks, generalizations, and to what can we actually apply this? So this was now one margin. The multi-margin case works basically analogously, and it is in the paper. It's just more technical. From the methods, it should be possible, so I'm no expert on that, but it should be possible to relax the assumptions on G. So we didn't have strong assumptions, but it was somehow bounded from above and upper semi-continuous, so you can probably get away from these, make them weaker if you work harder. And you can also include partial information, but not at the terminal time. At the terminal time, you need to know all call prices. This is related to some compactness principle that you need. But in the margins in between, you can know 0 to all call prices. You can even say at times 3, I don't know any call prices. That's also okay. Yeah, so examples is, of course, anything that depends on the price at these finitely many times and the quadratic variation at these finitely many times. That's okay. Anything that depends on the maximum, so like in these look-back options by Hobson. Any such integral where you integrate against the quadratic variation, you have the quadratic variation here and the process here. And then, okay, you plug it still into a function. Or anything that you can get by combining all these together. These are all fine. What is not fine, and this is something you can do with Duality-Sona, but not with us, with our methods, is such an integral, so an Asian option where you look at the time average, where you really take the physical time, because we apply this time transform that normalizes the quadratic variation. And this thing here would not be invariant under that. So this is not okay. But then again, so in real life, we don't have such integrals. We have finite sums. And once you turn it into a finite sum, it only depends on finitely many guys, and then you're in this setting again. So a discretely monitored Asian option would also be okay. Okay, so from my understanding, we cover anything that could be of practical interest, as long as you have one asset. If you go to higher dimensions, this thing breaks down completely because Skårhøjde embedding, which is the driving force here, and this Dambis-Dubin-Schwarz theorem as well, they're one-dimensional tools, and so there's no hope to do this directly in higher dimensions. But in one dimension, I think it's a nice result. Okay, yeah. So let me conclude. So we saw that this pricing hedging duality comes up again and again, and in many different shapes and forms. And in the model-free context, it is usually derived using the Skårhøjde embedding approach, but you need a new argument for every new derivative. So you cannot get a general result. Then there's the general approach of Dolinsky and Sona, with which you can do really a big class, but then you need so strong continuity assumptions that many of the ones that could be treated in the Skårhøjde embedding approach did not fall into there. And so what we did is we somehow, on a conceptual level, we combined actually these two approaches. So this optimization point of view, martingale optimal transport point of view, and this Goldhaut embedding point of view. And bringing these two together, we could get a result that in one dimension covers everything that these two cover, essentially, except the example of the continuously monitored Asian option. Thank you.
Other questions, remarks from the audience? Yeah, Costas.
So at some point you said that for typical price paths you can have a version of Ito integral. Is this correct?
Yeah.
So the question is, if you restrict attention to typical price paths that you can define the Ito integral, can you get away from the lim inf of hn.s and use those?
Yeah. No, I don't know how. So it would be very interesting, but I thought about it a bit, but it's not obvious at all. No, and also we can only do Cadillac strategies so far. So some of this, not so much. You cannot really take any closure also, so I think it would be very difficult. Yeah.
So in the beginning you actually mentioned some quasi-sure analysis with respect to measures that satisfy NA1.
Yeah.
But later on you talked about only pathwise.
Yeah.
So how do they...
So, I mean, it's pathwise, but what I'm saying is if you show that the outer measure of some set is 0, doesn't mean, of course, that the set is empty. So pathwise would mean the set is empty. If you show that the outer measure is 0, then it means that it holds quasi-surely. I mean, so it's a null set under all NA1 measures. So in that sense.
Questions? Okay, so thank you again.